Good day, everyone. Do you ever know what bioenergy and biomass is? Or do you use the two terms interchangeably? Well, lucky you, because in this lesson, we will learn about biomass as a resource, its conversion pathways and technologies, its products and applications, and last but not the least, its benefits and challenges. Bioenergy is derived from biomass, which are composed of recently living organic materials such as plants, agricultural residues, organic wastes, and algae. The US Department of Energy defines bioenergy as energy produced from biomass, which contains chemical energy originally obtained through photosynthesis. Bioenergy conversion is important because it provides a renewable alternative to fossil fuels. It also supports decarbonization by potentially reducing greenhouse gas emissions, and it provides waste valorization by converting organic waste and waste streams into useful energy and products. This presentation covers the definition of bioenergy and biomass, which I already discussed, examines biomass as a resource, explains the main bioenergy conversion technologies, discusses products and applications, and lastly, evaluates the benefits and challenges and sustainability considerations of bioenergy conversion. Biomass as a resource. Over here, we have three main classifications. We have the types of biomass feedstocks, we have biomass composition and characteristics, and lastly, we have the availability and sustainability of using biomass. So let's go to the first classification, which is the types of biomass feedstocks. Over here written, we have crop wastes, forest residues, purpose-grown grasses, woody energy crops, microalgae, urban wood waste, and food waste. So, mao na siya ang mga nakasuwat diri no, but overall, tanan nga organic material that can be considered as biomass. Most solid biomass is lignocellulosic. It means it is composed mainly of cellulose, hemicellulose, and lignin. These three components determine how easily a biomass can be broken and converted. Key characteristics such as moisture content, ash content, particle size, and contaminants strongly influence conversion performance. For example, high moisture content lowers combustion efficiency. However, high ash content can cause operational issues in reactors. Availability and sustainability. Although biomass is considered renewable, its sustainability depends on supply management and responsible harvesting. There are competing uses, especially between the food and fuel production. Land use chains, logistics, and supply chains must be managed carefully to ensure long-term environmental and social benefits.
Good day, everyone. Now that we understand what biomass is and why it is important, we can move on to conversion pathways or technologies. These pathways describe the different methods used to convert raw biomass into usable energy, fuels, and value-added products. In this section, we will discuss the main types of biomass conversion technologies and how each pathway works. Conversion pathways transform biomass into energy, fuels, and value-added products. Biomass cannot be used directly in most energy systems. Instead, it must undergo specific conversion pathways, which are classified technologies and processes designed to convert raw biomass into usable outputs. Three fundamental types of conversion pathways or technologies. 1. Biological or biochemical conversion uses microorganisms or enzymes to convert organic matter into energy products. In this pathway, naturally occurring biological agents such as bacteria, fungi, or enzymes break down biomass under controlled conditions. Common biochemical processes include fermentation, anaerobic digestion, enzymatic hydrolysis. These processes are typically operated at low temperatures and pressures, making them suitable for wet biomass, such as agricultural waste, food waste, or sludge. The main products of biochemical conversion are biogas, biomethane, bioethanol, and biodiesel, which can be used as fuels or energy sources. 2. Thermochemical conversion. Thermochemical conversion uses heat and sometimes pressure to break down biomass into simpler chemical components. This pathway relies on high temperature processes that rapidly decomposes biomass. Key thermochemical processes are combustion, gasification, pyrolysis, or liquefaction. Now, during thermochemical conversion, biomass is transformed into products such as heat and electricity, syngas, bio-oil, or biochar. This pathway is mostly suitable for dry, solid biomass such as wood, residues, and crop stalks because of its high energy output and fast reaction rates. Thermochemical conversion is widely used in large-scale energy production systems. And 3. Chemical or physiochemical conversion uses chemical reactions and catalysts to transform biomass derived materials into fuels or chemicals. Unlike biological conversion, this pathway does not rely on microorganisms, but instead on controlled chemical processes. Example of chemical conversion processes: transesterification, catalytic upgrading, hydrothermal liquefaction. These processes are commonly applied to biomass intermediates such as oil or syngas to improve fuel quality. The output includes biofuels, chemicals, and upgraded solid or liquid fuels that can directly replace or supplement fossil-based products. Overall, this pathway focuses on enhancing and refining biomass-derived products into higher-value fuels and chemicals. Selecting pathways and typical process flow. When choosing a biomass conversion pathway, not all methods are suitable for all situations. And pathway selection mainly depends on 3 key factors. That would be feedstock type, desired product, and process efficiency and environmental impact. Now, the type of characteristics of biomass strongly influence which conversion pathway is most appropriate. Like for wet biomass such as food, waste, manure, or sludge is better suited for biological or biochemical conversion, since microorganisms require moisture to function. Dry, solid biomass, like wood, crop residues, or husk, is more suitable for thermochemical conversion, which relies on high temperature. Biomass that can be processed into oils or intermediates may undergo chemical or physiochemical conversion for further upgrading. This means the physical and chemical properties of the feedstock determine how efficient it can be converted. The selected pathway also depends on what output is needed. If the goal is heat or electricity, thermochemical process such as combustion or gasification are often preferred. If the goal is liquid fuels like bioethanol or biodiesel, biochemical or chemical pathways are more appropriate. If the objective is byproducts or chemicals, chemical or physiochemical conversion pathways are typically used. Another important factor is how efficient and sustainable the process is. Some pathways offer high energy efficiency but may require higher capital costs. Others operate at lower temperature and may have lower emissions, making them more environmentally friendly. Environmental impacts such as greenhouse gas emissions, waste generation, and resource use are considered when selecting a pathway. The goal is to choose a pathway that maximizes energy while minimizing environmental harm. Products and application of biomass conversion. The products of biomass conversion show how biomass is used in real-world energy systems and energies. Depending on the conversion pathway used, biomass can produce energy, fuels, materials, and environmental benefits. Like for example, heat and electricity generation. One of the primary applications of biomass conversion is the production of heat and electricity. Biomass can be directly burned through biomass combustion or combined with fossil fuels in coal-firing systems to generate thermal energy. This heat can be used to produce electricity in biopower plants. These systems provide renewable energy that can be used for residential heating and electricity, industrial processes, supplying power to electrical grid. By replacing or supplementing fossil fuels, biomass-based power generation helps reduce greenhouse gas emissions and increase energy security. Liquid fuels or biofuels. Biomass conversion also produces liquid fuels, commonly known as biofuels. Like ethanol, usually blended with gasoline, biodiesel, used in diesel engines, drop-in fuels, which can directly replace conventional aviation, diesel, or gasoline fuels without major engine modifications. These fuels are used as alternatives or supplements to fossil fuels, especially in transportation sector. Byproducts and chemicals. Beyond energy and fuels, biomass conversion also produces value-added byproducts and chemicals, like bio-oil, which can be upgraded into fuels or used as a chemical feedstock, syngas, used for power generation or chemical synthesis, biochar, used in agriculture, soil improvement, and carbon sequestration. These products serve as material and chemical feedstocks for various industrial applications, reducing reliance on petroleum-based chemicals. Waste management and circular economy benefits. Biomass conversion plays an important role on waste management and the circular economy. Agricultural waste, municipal organic waste, and biomass residues that would otherwise be sent to landfills can be converted into energy and valuable products. These processes include reduced landfill use, minimize waste disposal problems, promote resource recovery and rescue. By turning waste into useful outputs, biomass conversion supports a circular economy where materials are continuously reused instead of discarded.
Benefits and challenges. Benefits of biomass conversion. Renewable and sustainable, reduces reliance on fossil fuels. Carbon neutral potential, lower net greenhouse gas emissions. Waste reduction converts agricultural, municipal, and industrial waste into energy. And energy security, diversifies energy supply and supports local economies. And multiply product output, produces heat, electricity, biofuels, and bioproducts. And the key challenges. Number 1, feedstock logistics. Collection, transportation, and storage can be costly. Number 2, technological complexity requires efficient and scalable conversion systems. Environmental trade-offs, land use, water consumption, and biodiversity impacts. And economic viability, high initial investment and competition with fossil fuels. Lastly, policy and market barriers, inconsistent regulations and subsidies. And a conclusion, biomass conversion, a key pillar of the renewable energy future. Biomass offers a versatile and sustainable pathway to produce energy, fuels, and bioproducts, while challenges remain in technology, logistics, and sustainability. Ongoing innovations are improving efficiency and reducing impacts. Integrating biomass into the energy mix supports climate goals, waste management, and energy independence. Call to action. Continued research, supportive policies, and public awareness are essential to unlock the full potential of bioenergy and a circular, low-carbon economy. Thank you.